So back in grade 9 and grade 10, you did a lot of work on finding the slopes of lines. And so that was trying to put a number to how the thing changed, right? Rise over run. And then in grade 10, you did a whole bunch of work about parabolas. And then in grade 11, you did a whole bunch of work on other functions, like the exponentials and the rationals and the sines and the cosines. And not once did anybody say anything about slope for those curves. And if you take a look at this parabola I've drawn for you here, you maybe can appreciate why. The slope of the parabola here, I don't know what the number is exactly, but it has an upward slope. And here, it has an upward slope, but if I grab a marker there, it's not as steep as it used to be. And in fact, at the vertex, the slope of that thing is 0. And then after the vertex, the slope goes negative. So the reason you didn't talk about slopes for those other functions is that the slope of those functions is different depending on where you are. And up until that point, or up until this point, you haven't had the algebra skills you need in order to actually determine the slope of one of these curves at any particular place. So we're going to do a really clumsy version of it. And if you want a more elegant version, you should take the calculus course, because that's the entire purpose, well, half the purpose, I guess, of calculus, is to determine the slopes of exotic functions. But we're just going to do some numerical examples here to get ourselves warmed up as a pre-calculus event. So the thing I'm going to start with then to try and get this done is to start with the slope of a secant to this line. So let me jot that up there. Slope of a secant. Now, a secant is a line that just cuts through the function. So I might draw one from here to, let's say, here. So there's my secant. 2, 1, 2, 2. Like so. Okay. So if I'm going to do a slope, I need to have the rise, so how much the function goes up or down, and then I have to divide it by how far it takes to do that. So in this particular function, I have a triangle forming, if you can see that there. Got this little piece here, drops that much, and then it runs that far. Now I could just count those because I happen to pick convenient places. But if I were to try and do this algebraically, the slope, change in y over change in x, I'm going to have to figure out how high this is, first off. So to figure out how far up you go on a function, you just need to take the x value and plunk it in for x and do some calculating. So this particular place is when x is 7, and this particular place is when x is 1, 2, 3, 4, 9, 10, 11, 12, 13. 1, 2, 3, yeah, 13. So I'm going to be determining the slope of a secant on f of x between x equals 7 and x equals 13. Okay. So in order to find out this height here, I'm going to have to take the function and I'm going to have to evaluate it at 7. And then I'm going to have to take the function evaluated at 13. And I'm going to have to subtract the two values. So this thing drops, right, is the difference between here and here. Underneath, I'm going to have to take the gap that this thing goes horizontally. So it goes from 7 to 13. Okay, so to do a little work here, the function at 7 would be negative 1/4 of 7 minus 9 squared plus 11. So 7 minus 9 is minus 2. Minus 2 squared is 4. And minus 1/4 of 4 would be minus 1. Minus 1 plus 11 would be 10. So when I work this out, then the slope f at 7 is 10. Now I still need to evaluate this thing. 7 minus 13 is minus 4. I'm just going to erase this then. And I need to get the function at 13. So that would be negative 1/4 13 minus 9 squared plus 11. 13 minus 9 is 4. 4 squared is 16. Quarter of 16 would be 4, so I end up with negative 4 plus 11, which equals 7. So the value of this function here at 13 is 7 high. Right. So to finish off here then, 10 minus 7 would be 3, or negative 4. So I end up with a slope for this secant of negative 0.75. Or you could leave it as this fraction. Slopes are sometimes more useful as fractions. And if we check here, this thing drops 1, 2, 3, and over. Something funny happened there. 1, 2, 3, 1, 2, 3, 4. Hello, friends. 7 minus 13 is 6. So that's negative 1/2. So if you can actually do algebra correctly, or I suppose in my case it was subtraction correctly, you can see this line is dropping 1/2, dropping 1/2, dropping 1/2. Right? So all we've done there in order to get the slope of a secant between these 2 points is to evaluate the function at the start, evaluate the function at the end, and then subtract the start x from the or the final x from the start x, and you get a slope. One awkward cut, and 4 years later, we're going to try and actually write the equation of this secant. So some facts from the distance past when the first part of this video was crafted. I have a parabola here, that's its equation. And I think just from the graph, we figured out that the value of the function at 7 was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the value of the function at 13 was 1, 2, 3, 4, 5, 6, 7. And there was a bunch of work here where we learned that the slope, delta f over delta x, of the secant was negative 1/2. Okay, so with all that information gathered, if I'm trying to draw the equation of a line, I start with the same basic format we've always had for lines, y equals mx plus b. Now, in this particular case, because I'm drawing a secant on a curve, the slope I'm going to use is this df by dx. So I'm able to fill in my negative 1/2 here. Now, in order for this line equation to be finished, I need a number sitting in here for b, which serves as the y-intercept. Now, I could track this back graphically, I could do that, or I could calculate it using this pair or this pair. If you look at this setup here, as long as I have an x and a y, I can dump them in, and the only variable left to solve for is b. So I'm going to try this first pair here. 10 is my y value, 7 is my x value, half of 7 is 3.5, kick that over, 10 plus 3.5 is 13.5. So the equation of that secant then is negative 1/2 x plus 13.5. And if I sort of look where that's going, it's going to hit about here, which according to this grid is 12, 13.5. It's all going to work out. If you're not sure about choosing this pair, you want to choose this pair instead. That's okay. Questions are always good. If I put in 7 as my y value and 13 as my x, half of 13 is 6.5. Kick this to the other side. 7 plus 6.5 is, lo and behold, 13.5. So it didn't change the outcome, and that's obvious and important because these are on the same line. So as long as they line up that way, no matter which x-y pair you choose on that secant, you're going to get the same equation. So you have to go through that process, the rise over run process, to get your slope. And then once you have your slope, you're free to put in any xy pair. This one is convenient because you already calculated it while trying to get the slope. This one is also convenient because you also calculated it while trying to get the slope. But if you wanted to use this point here for some reason, if you could figure out its xy coordinates, you could dump them in and get the same y-intercept. We just use these two, one of these two dots generally because you already have them. All right. 4 years later, 10 minutes of video, and now you're ready for the practice problems.